2/2. We have the fill lamp, which is on 2/3. We have the full lamp, which is on 2/4. And what else do we have? Well, we have a solenoid valve, which is on 2/1. Let me move that one up here. Just plan ahead. Okay, so O:2/1 is the valve, and O:2/0 is the motor. Now, do all of the outputs depend on all of the inputs? Not really, right? You could say that the motor running or not depends on the start and stop button. That's true, but it also depends on the proc sensor and level sensor, right? So we could try to make a truth table that includes the start, stop button, the procs, and the level sensor to determine whether the motor should be on or off. But if we did that, how many combinations of the inputs would we have to look at? We have 4 inputs, that would be 4 bits. How many different numbers can you make with 4 bits? Like 16, right? Because 2 to the 4 is 16. We would have to look at 16 different inputs to determine the state of the output. Most of the time, that's not really the way we want to do it. Okay? Really, the start and stop button don't start and stop the motor, they start and stop the system. So how about instead of using truth table programming for the start and stop button, how about if we just do what we've already done and use a seal insert? Okay, so we're going to use a little bit of glue code, or C advanced programming, but then we're going to use truth tables for the rest of it. So what I'm going to do is create a seal-in circuit, not based on the motor, but based on the run lamp. Because the run lamp basically just indicates when the system is on, not when the motor's running, right? So I'm going to use an output that is the run lamp. I'm going to use an OR around the start button. And since the stop button, as usual, is a normally closed stop button, I need a set of examine and closed contacts. And let's just, stop button is here. Start button here and seal in here. Okay. Now at this point, all that will happen is when I hit the start button, it'll seal in and turn on the run lamp. And when I hit the stop button, it'll shut it off. But essentially now the run lamp serves as a memory bit to tell me whether or not the system is running. Okay? And we're not going to use memory bits much yet. We'll use them in a minute once we find them, or probably next class. Once we find the truth table programming will be a little bit inadequate. Okay, so you understand what happens, right? You press the start button, the stop button being normally closed allows power to pass, run lamp comes on, run lamp seals, run lamp in, and away we go. We hit the stop button, breaks the seal in, and turns off the lamp. Okay, so standard seal insert. I don't have to deal with truth table programming for the start and stop button. Basically now I have a lamp address on output 2/2, which I can reference to decide whether or not the system is running. Okay? All right. Now that's helpful. So basically, I don't want anything to happen unless the run lamp is on. So as I add rungs, what I'll do is I'll probably simply put a set of contacts on each rung referencing that lamp so that the rungs will not actually run or do anything unless the lamp's on, unless the system is in the running mode. Okay? Now, let's go on. We've kind of sidestepped the issue of truth table programming so far. But let's go on and decide what should happen. The motor running. What does the motor running depend on? Well, first of all, whether or not the system is in the run mode, right? But we're going to include that by default by putting the run lamp on all the rungs. So we don't have to worry about that as a benefit. Well, what does it depend on? Well, it depends on whether or not a box is present and whether or not that box is full. It essentially depends on 2 things, procs and level, right? So the inputs are essentially procs. In fact, let me put them up here. Let me erase them, or I'll just move it up. I'm not going to use the addresses themselves. I want to think about how I want this system to work. Okay. The only output I'm going to program based on prox and level right now will be the motor. So outputs, it'll just be a single output. So motor is the only output I will program. Now if I have 2 bits, prox and level, how many different combinations are there? 4, right? There's off, 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 on, off, and on, right? If prox is off and level is off, should the motor be running or not? Well, if prox is off and level is off, it means we don't have the box. So yeah, we need the motor on. So let's put a 1 there. Not motor. If prox is off but level is true, what does that mean? Probably that we've got a problem, right? It means that this level sensor shouldn't be on, right? So in that case, we really don't care. Let's just say that motor is on at that time, right? Because apparently something's wrong. We just need to keep the system running. Maybe everything will correct itself. Okay. What about if prox? That's a hope that doesn't ever pan out. But anyway, what if prox is on and level's off? Well, that means we've got a box in place that's apparently not full, so we need to stop. Right? So in that case, we want the motor off. And lastly, if prox is on and level is on, tell me intuitively, what does that mean? What's that?
The box is full and
The box is full. So it's ready to move on, right? So the motor should be on. Okay. So this is the truth table. And we can program this pretty straightforward. Have you guys seen cardinal maps before, ECETs? Well, it doesn't matter. Basically, you program once. The way you can do this is look at it and decide what are the conditions for the motor being on. Well, these are the conditions. Now, I'm a little rusty on this, so let me think for a minute. What's the best way to describe this? If prox is off, then it doesn't matter whether level is on or off, right? It could be off, it could be on, we want the motor to be on. Okay? So to program this, what I might say is motor is the output. If prox is not true, motor should be on. That's basically what this says. Right? Prox not true, motor will turn on. On the other hand, if prox is true, like here, and level is true, then I want the motor to be on. Does that make sense? See how that represents all these ones? Because look, if prox is true but level is not, this will be made, but this won't, and the motor will be off, which is what we want. So essentially, you program once in this one. Okay? So we're programming once. Now, there's a fancy way of programming the single zero and then inverting it. Okay? But we'll worry about that a little bit later. So this is the code that I'm going to use, and basically what I've done is I've used a truth table to program an output. Okay, so let's do it. So the output I'm going to deal with is the motor. And I essentially need to set up the structure that I've reasoned out here from the truth table. If prox not true, prox true, level not, no, level true. So let's see, prox goes here, it also goes here, and level goes here. Let me add some comments. Okay. So far so good. So that's how we program the motor. You guys need a minute to copy it. You're welcome to if you want. I will post this program for you as well. Questions, problems, comments? Now, what determines whether or not the solenoid valve should be on? Be careful here. You might be tempted to say if the motor's off, that would be a condition. I'd like to avoid that if I can, and I'd like to only use inputs. In fact, I could use just these inputs to program the solenoid valve. Because in the case where prox, notice we've only got 2 inputs, so this is going to be pretty straightforward, right? When prox is not true, then the solenoid valve should be on, right? Because prox not true means there's no box to catch the stuff, right? So I want the valve to be on. On the other hand, if prox is true, if there's a box in place, but that box is full, I don't want to try to overfill the box. So that's another case when I would not have the valve on. In fact, basically valve looks like the inverse of motor. Okay. This is a fairly simple system, so it's not a surprise that that happens. Okay. So all I have to do is program a single one. It's this one. When prox is true, level is not true, valve should be on. Okay, so let's do it. I need another rung because I have a new output. By the way, in Logix Pro, be careful about dragging something to the end rung. Sometimes it will simply disappear. Also, one other hint with Logix Pro, save often. Sometimes it will just delete all of your comments or some of your code, and it's not very friendly. Okay? It doesn't even have an undo button, which really stinks. But that's reality. Anyway, insert a rung, it'll save you time. Most of the time it works to drop it onto the end rung. It'll make it a rung for you. Sometimes it just blows away all of your code. All right, so put what am I doing? Not motor output, the solenoid valve output. Edit symbol, call this valve. The conditions for valve being true, well, our default condition is that the run lamp has to be on. We don't want any of this code to execute without the run lamp being on. But our decision was that we want prox true, level not true when the valve comes on, or for the valve to come on. So we want prox true, in other words, a box in place that is not full. Now, we haven't programmed the fill or the full lamp, but it's pretty easy to add those in. Those are two more outputs that we can add. Let's think about it. How do we know the box is full? Well, the only way we know that the box is full is if level is true. So full would be true anytime level is true. That's going to be a really easy one to program. Other than that, it's off. Fill is only true when we're filling it, so that would be similar or look exactly like the valve. Now I'm going to show you a trick. And we might break this a little bit later, but I'm going to show you a trick. Since valve and fill have the exact same logical structure, then what we can do is add an output by ORing around the valve. Okay, this is the way I prefer to do it. I'm going to show you another way to do it, but this is the way I prefer. And I'm going to put the fill lamp. What this will do is anytime the same conditions are true that turn the valve on, it will also turn on the fill lamp. This is the way I prefer you to set it up. If you're going to have two outputs on a single rung, I prefer that you set it up this way. You could set them up where they are in series, one after another, but if an electrician looks at this as if it's a schematic, he's going to go, what the heck is this? Because you've got half the voltage drop across one of the outputs, and the other half across the other one. That makes no sense to you, okay, or her. It's much better to put it this way so that you're hearkening back to electronic schematics, or basically not wiring diagrams. There's a special name for it, I can't think of it. When it's set up like this, where you've got two rungs of power, then there's a name for it, but I can't think of what it is. Okay? But I prefer to see you do it that way. If you want two outputs on a single rung, do it with an OR rather than an AND. This will work. Okay? You can do this without the OR. But I prefer to see this. Okay? All right, now the full lamp is a little bit different. Its conditions are that it is true when level is true. Notice it doesn't care whether or not prox is true. It's only true when level is true. So that's a very straightforward output. Really simple. We'll add another rung. Basically, the full lamp will be on. When the level sensor is on. Now let's see if our code works. Are you ready? Download, turn down the scan speed so it goes nice and slow. Run, nothing happens. Why? Well, we haven't hit the start button. Let's hit the start button. It goes nicely. Oh, something's wrong. Pouring product all over the floor. Stop. What happened? Well, something very important happened. The box moved over. It started to be filled. It was full. This level sensor was triggered. We turned on the motor, we turned off the valve. But then we got to a condition. This looks like an empty box condition. That's basically what condition? Proc's true, level not true. It's this one. It says shut off the motor and fill it. Somebody poured Pepto-Bismol all over the floor. Okay. I've done it a million times. Okay, that's normal. It's okay. Don't worry about it. Okay, you're going to do it too. Everybody in this room will probably do that. That's fine. Okay. I call it Pepto-Bismol because it's painless. This looks like. I don't know why we're filling boxes with Pepto-Bismol. Whatever. Okay. I think we'd have a lot of leaks, especially if they're fire. So this is a condition we didn't think about, right? It turns out that the level sensor is offset from the proc sensor. So this idea of truth table programming is fairly straightforward. It kind of worked. It might help us get started, but it didn't solve the problem completely. We're missing something from the truth table. We're missing memory. Notice that the seal-in circuit is essentially memory, right? It's something that remembers that an event happened. Notice what happened. We press the start button, and the run lamp stays on because we remember that we press the stop button, or the start button. The run lamp serves as a memory bit. Now you don't have to use an actual output as a memory bit. You can use a bit that's actually in memory in the bits file or in the integers file. You can reference an address other than an output and just turn a bit on in memory to remember that something's happened. Now, something important happened. We needed to remember that something happened. What was it that we should have remembered? What happened that was important? More Pepto-Bismol on the floor. All of you are going to do it, trust me. It's just fun to make Logix Pro do that. What happened? What was the event that happened? Because notice now, with this set of inputs, our output desire is different, right? We actually don't want the valve to come on and the motor to turn off when prox is true and level's not true. What happened? We filled the box. Right? We need to remember that this happened, that there was a box and that box was full. So basically what we need to do is set a bit in memory somewhere, and it'll look a lot like this seal-in circuit. So we're not going to program the output of this bit. We're not going to program it with the truth table. We're going to program it more like the seal-in circuit. Okay? We're going to select a bit in memory. That means that there's a box full. Now, what we might do is instead of selecting a bit in memory, we could use the full lamp to do this. So I'll probably go ahead and do that, and then I'll actually use a bit later. Let me go ahead and show you again where the bits are. I could use a bit in memory, like say, I don't know, this bit, or this one, or if I scroll down, this one. It does not matter. They are there for me to use. They are just memory bits. All I have to do is select an address. Say I want to use this one, because I can reach it if I want to it. Bit 5/15. Fine. I could use that as an address instead of any of these outputs and have a rung that controls that bit. Okay, I'll have to add another bit to do it. But for the sake of using only outputs right now, let me instead use the full lamp as a bit to remember that there's a full box. Okay, so the full lamp was very simplistic before. Okay, it was just triggered based on level. I don't want that. In fact, I forgot to include my run memory address there, and there may be a reason for not wanting that. I'll show you that in just a minute. Okay? I don't necessarily want this here, but we'll come across that. Basically, this is going to kill all the code if the machine is not going to run straight. So here's our full lamp, and basically what we want to do is have it seal itself in when a certain condition occurs. We want it to come on when both prox and level are true. Level's true and prox true. That is a very particular condition. It should come on when that condition happens, and it should stay on even when that condition is clear. Okay? So we have to OR around this and include a set of contacts so that it will stay on, right? So as soon as prox is true and level is true, we know the condition that has occurred, or the event that has occurred, is that we've got a full box. And when that happens, we want to OR around it to remember it. Okay? Now, the thing about seal-in circuits is you have to always decide what turns it on and what turns it off. Just like with the start-stop button. What turns on the seal-in circuit is the start button being pressed. What breaks the seal-in is stop being pressed. Notice in the normal truth table when we're programming an output, we program outputs based on inputs, and we only have to program ones. We don't have to program zeros. If you're programming something with memory, you have to program the zero or what shuts it off. So what should shut off? When should we forget that there's a full box?
Box leaves.
When the box leaves, right? In other words, when the prox sensor shuts off, that's what should break the seal-in. Okay? So basically, we need a condition here of prox true. Another way of doing that is by simply pulling prox out. Okay? But for the sake of what we're doing, to make it really simple to understand, I'm just going to put in a set of contacts that reference the proximity sensor itself. Okay, so set of contacts, prox sensor, there is a simplification we can do, don't worry about it right now. As soon as the prox sensor and level sensor are both true, then full will come on, we'll seal in. Even when level shuts off, we will remember that we've got a full box. Okay? And then what will happen is as soon as the box clears, the prox will go off, that'll break the seal in. Okay? Now we haven't set it up yet where this will work, we just set up the memory. So what do we need to do? Well, now we actually need to use this memory bit, and I'm kind of sorry that I used an output for that. Let me change that, I don't know. Let me change that and do it this way. Because that's really bad programming. I'm going to make the lamp depend on a bit address. I will simply choose bit, d:0/0 is an easy one to choose. And I'm going to say full box event. Okay? This bit will be on. We're going to seal it in right here. When a full box event occurs. Does that make sense? Prox and level being on represent a full box event that will seal in, and that's when we'll turn on the output lamp. The reason I'm going to do this is because I want to use this bit now as an input to decide when the motor should be on or not. So I have to expand my truth table. I've only got one more piece of information, one more on-off piece of information. Full bit, but that bit will add twice the complexity of what we had before. Because now I have to consider, again, all the possible combinations of the other inputs. Okay? Because now I have 3 bits and I have 8 possible total combinations. Now let's go back and check this and make sure this is correct. If we have not observed an empty box and prox is off and levels off, we want the motor on, we want the valve off, we want fill off, and we want full off. That still makes sense. If we do not have a full box and prox is not true, level is true, something's weird. Hopefully we never actually observe this, but we may as well just leave the outputs as they are, because we really don't care. We don't really expect to observe this. Now, for those of you that have programmed real PLCs, you know that this is where you start with errors, right? This is where you say, wait a second, that's a combination that should not be possible. That, and the big side of PLC programming is how do you deal with things that should not happen when they do happen, okay, and error check. We're not going to get into that in this class, unfortunately. We simply don't have the time. You have to learn the syntax, you have to program some projects. But in the real world, PLC programming is even more complicated than this. Honestly, this course is simply an introduction to PLC programming. So anything you guys that have programmed PLCs, anything you want to add, I'd be glad to hear it. Okay? And it'll enrich the course. Okay, so now let's continue. Oh, by the way, ladder logic is not the only way to program PLCs. There are many other ways. Okay? But this is good because it's more about training your brain on how to think. And ladder logic is still pretty common. So anyway, if the full bit is off, prox sensor true, level sensor not true, we know we're not in this condition because we're going to remember the condition where we've got a full box, right? But we don't have a full box, so it's okay to go ahead and fill it with the motor off. Okay? We'll turn on the fill lamp, and that makes sense. If full bit is not true, prox is true, level's true, then what do we want to do? Well, we want to turn on the motor, not turn on the valve, and full lamp on. Now notice, this will only happen for one scan, because as soon as prox and level are known to be true, this bit is going to be sealed in, and now the full bit will actually be on. Okay, so this condition can occur, but it will only occur for one scan. The next time the PLC comes back through the code, the full bit is going to be on because it will get evaluated to be on, it will be turned on. Okay. Now, let's continue. If the full bit is true, prox is not true, level is not true, this also will only occur for one scan, because any time prox is not true, this bit is going to be shut off, and we'll be back up here. Does that make sense? So we're not terribly worried about what happens here. We can essentially program based on prox and level, but we'll consider the fact that we've noted a full box. If we had a full box but prox is not true, it's time to bring another box into position. Right? So anytime there's not a box but there was a full one, we're going to forget that next scan, and it's time to get another box in place. So those would both be ones, and they look exactly like they did before. Okay. How about level? Well, let's see. If level is not true, motor's on, valve is going to be off in both of these cases because we've got a moving box. We're not filling, and we would have a full box, so we should program that on, even though it's going to shut off next scan. Program it on here, fill's not true, so there we go. We only have 2 more lines to program. All right, I'm sorry, I see I'm running late on time, but let me just finish this quickly and then I'll close it. Okay, so when the full bit is on and prox is true, but level is not true, that's the condition. That's the whole point of adding this bit, right? It's when we remember that a box was full, prox is true, level is not true. What do we want to do? Well, we've got a full box. We don't want to try and fill it. We want to keep the motor moving and leave the valve off. Okay? We are not filling, we have a full box. Okay? What else? Well, when the full bit is true, prox is true, and level is true, that's only going to happen for a short period of time, because that's the time when the box has been sitting under here, it's full, and now the full bit has been triggered, and so the box is now moving. Now, another trick to PLC programming that's very important to remember is that you need to think in terms of what's going on in the PLC speed versus mechanical system speed. Mechanical system speed is typically much slower than the PLC speed. So the PLC is going to feel like it's waiting forever for the box to move out of the way. Okay, it's going to say, okay, we still have a full box, new scan. Still have a full box, new scan. It's going to be waiting for a long time for this box to move out of the way. Okay? So for a long time, the PLC is going to see level true, prox true, and remember that it had a full box. It's going to be scratching its head going, what's going on here? Come on, let's get this thing moving, right? Okay, so we need the motor on, we need the valve off. We don't want to fill or indicate it with filling, we want full on. Okay? Now notice that the full lamp right now is essentially programmed to follow the full bit, but we've got a single one here and a single one here that does not follow the full bit. Is it really worth it, though, to program these ones? Probably not. The full bit really indicates when the box is full. This set of conditions is just going to happen for one scan, because if prox is true and level is true, then very quickly the bit's going to be set and we're going to be down here. Okay? So I don't really care. I'm just going to make that a 0, because a single scan in user time is not much time. The user's not going to notice the difference with the light being on or off. So I'm just going to make that a 0 to make my life easier, okay? So that I don't have to program that condition. I'm also going to make this a 0 to make my life easier, because if level's true and prox is not true, something's wrong somewhere. So I really don't care if this is on or off. So for the sake of making my life easier, this makes the full lamp simply follow the full bit. Makes it easy. Okay? All right, so what do I really have to do here? Well, basically what I have to do is make motor depend on full bit and not just prox and level. Okay? So the motor should be on in the case where I have full true, prox not true, level true. Okay, so I can modify the code pretty quickly. This is fairly intuitive after you get used to it. Motor should be on in another condition, and that is when prox is not true, level is true, and full bit is true. So all I have to do is add another board. This is when prox is true, level is not true, and, it's a logical and, the full box event has occurred. That should make the motor come on. Now for the valve, notice I do not want the valve on in this case. So another condition for the valve being on, since I only program once, is that the full bit be off. So that's simple to add. All I have to do is add one set of context that says full box event has not occurred. Let's try again. Let's clean up the mess. Simulation, reset simulation. Okay. You know what? I've done a lot of work. I'm not practicing what I preach. I said save often. If I lost this now, it would be catastrophic. Silo with memory. Take me a little bit of time to read that. Okay, download, run, start, fill a box, fill a bank. There we go. So now we have a line that fills boxes without pouring product all over the place. Okay? I can stop it. Let me show you one more problem. If I stop it here and start it, works, that's nice. If I stop it at just the right place, okay, let's see what happens. Well, if I stopped it here, I think everything will be okay because prox and level are true. If I can get it to stop at just the right point, we've got a problem. If I can stop it, I'll have to describe it because I'm out of time. If I can stop it right here where prox is true and level is not true, consider what happens to the bit. If I stop it at that point, because I've got this run lamp in there, the system is going to forget that it had a free box because this shutting off will also break the ceiling. If that happens and then I start it up again, the system is going to pour product all over the floor again because it's going to see a box in position by prox that is not full by level. And so it's going to start the flow up again because it does not remember that there was a full box. So in my coding, I would actually recommend that we remove this. Does that make sense? Because if I remove it and happen to stop it at that position, it will still work. So program, run lamp, pull it out. That's what I would actually suggest. A lot of times, you do not want to clear memory bits when you stop the system. You want the mechanical system to stop, but you want to keep memory intact. Memory bits. Okay? Make sense? I know that's a lot to take in. I will help you guys with this. Programming the door simulator and the silo simulator is part of your homework for the next step. So those of you that are done with homework 1 can go ahead and get started on that. It should be pretty straightforward for those of you that are familiar with this. Those of you that are not, don't worry. There's a very wide range of skill levels in this class. I'm shooting for the lower level. That's what most of you are. So don't panic. I'm not going to run away from you. All right. Thank you for your patience. I'll see you guys next year.